Alright, now that we have a little better idea of how these electrons exist in atoms, let's talk more specifically about how we can represent these electrons in orbitals and electron configurations. And they are slightly different. The orbital diagrams, as you'll see, have us doing up and down arrows, and then the electron configurations. Hopefully you've done this before, the 1s2, 2s2, 2p6 stuff. I know they've moved away from it in high school, or at least they've modified it to be just 2-8-18, a bunch of nonsense. So if that's what you're used to, this will be a little different, but hopefully you've had this sort of electron configuration and orbital diagram notation in the past. Alright, so before we can start filling in arrows to represent our electrons, we have to have an understanding of how electrons fill orbitals. So energy levels that we talked about before, the principal energy level, which corresponds to the horizontal rows in the periodic table, and then those columns have to do with the different type of orbital that's being filled. There are energy differences, and the electrons go by energy difference, so they fill in order of increasing energy. They begin with the lowest energy, the quantum number n equals 1, and first they would fill the s orbital, followed by p, d, and then f within each energy level, although as we mentioned already, we do see some unusual behavior like the 4s filling before the 3d. So within any given energy level, we fill the s, then the p's, then the d's, then the f's, but we can have some interesting things happening once we get to energy level 3 and beyond in terms of a 4s, for instance, filling before a 3d. Now this particular image doesn't do justice to the difference in energy levels, so that 1s should be quite a bit lower in energy than the 2s, and things should start to get closer together as we move up. So if you ignore that flaw in this particular graphic, what it does show is it nicely shows the orbital filling order. The 1s, then the 2s, then the 2p, then the 3s, then the 3p, and there you see that 4s getting in the way of the 3d, so that's why we fill the 4s first. It's lower in energy than the 3d sublevel. Then we go back to the 4p, and then we have the 5s doing something similar, getting itself in there and filled before the 4d, and so on and so forth. So that's why we tend to see the d sublevel appearing in the next principal energy level. So if you're looking for the elements with electrons in their 3d sublevel, you're going to have to look for periodic table horizontal row number 4, principal energy level 4. If you want to know where the 4Ds are, you're going to look in the energy level 5. The Fs are actually 2 less than the energy level you would expect. So the 6s fills before the 4F does. So just remember the Ds are appear 1 period later than you'd expect, and the Fs appear 2 period later. Because you fill the 6s before the 4f, you fill the 7s before the 5f. Okay, here we see an example of an orbital diagram, those boxes down at the bottom right. So an orbital diagram has the orbitals shown as boxes in each sublevel. So for the s sublevel, there's just the 1 box. For the p sublevel, as we can see, we have 3 boxes. For the d, there would be 5 boxes, and then for the f, there would be 7 boxes. So the electrons go in as vertical arrows. Usually we don't show double arrowheads, just a single arrowhead, but this graphic has the double arrowhead. If you move on in chemistry, that might be more important to follow the correct formalism, but for this course, double arrowhead, single arrowhead, I'll accept either. Electrons in the same orbital have to be opposite spins. So first we would fill the 1s orbital spin up, then we would go back and do the spin down. And then if we have another electron, like this case here, we see the example for lithium, we have 1 more electron, and that would go spin up into the 2s. And if we moved on to beryllium, we'd have another electron that would go spin down in the 2s, and so on and so forth. Now with our previous example, we only dealt with s orbital electrons, and that's pretty easy. We fill the lowest energy level first, and we completely fill the 1s orbital before we move into the 2s. If we have the p sublevel or the d sublevel where we have multiple orbital types for that particular sublevel, then we would half fill. So for the p's, for instance, we would singly fill up then we'd move into the next box, singly fill up again, then finally singly fill up, and then after we've half filled all 3 p orbitals, we'd move back and spin down for each of the remaining. Okay, so that's how we would approach something where we have a p or a d sublevel that's filling. So if you were thinking about, say, boron has no choice but to have the 1s up and down, the 2s up and down, and then the 2p up. And then as we move on to carbon, we'd have another up electron, and then nitrogen, we'd have all 3, and the p sublevel will spin up. And once we get to oxygen, now we spin down the first and fill that first box. We'd spin down the next box for fluorine, and then finally when we get to neon, everybody's completely filled. And so here off to the right, you see an example of the carbon orbital diagram that I just mentioned, where you have the 2 half-filled spin up p sublevels. So the first 4 electrons were easy to fill. Spin up in the 1s, then spin down in the 1s. Spin up in the 2s, then spin down in the 2s. The next electron has no choice but to go into one of the p's, and we ordinarily just move from left to right, and we do spin up first. The spin up is spin that's in the same direction as the magnetic field, and therefore it's slightly lower in energy than going opposite. So the big question was, what do we do with that next electron? Do we do spin down in that first orbital box and fill it, or do we move spin up into the next one? And obviously, as you can see, we would move into half fill all the boxes before we go back and pair them. Okay, so it only affects us with p and d sublevels, because s sublevel, there's only that one spherical orbital type, and we have no choice but to go spin up then spin down. But for p and d sublevels, at least in this course, we'll always have spin up until we half fill, then we'll go back down and spin pair with the spin down electrons. Interesting things happen with d sublevels if you go on in chemistry, but for our purposes, we'll just stick with the simple, typical cases. Okay, so this seems like a good point to take a break, have a chance for you to see how well you're tackling this material. We'll do a learning check here. So your learning check assignment is to write the orbital diagrams for each of the following. So the element nitrogen, then the element oxygen, and finally the element magnesium. So please pause the video now, and then when you're set, start it back up and we'll see how you did. Okay, so hopefully for nitrogen, you remember what I said earlier, and that's, of course, the 1s and the 2s, spin up, then spin down, then move up to the 2s, spin up, then spin down. And for the 2p sublevel, because nitrogen has a total of 7 electrons, the 4 that we've already used in the 1s and the 2s, and then 3 remaining, each one goes spin up in a separate p orbital. Now when we move to oxygen, it looks almost the same, except we have 1 more electron. Oxygen has a total of 8 electrons, to nitrogen 7. So we went back to that first, the leftmost p orbital box, and we put a spin down electron. If we look at magnesium, which has even more electrons here, a total of 12, we do the 1s, half fill, then fill it, 2s, half fill, then fill it, 2p, spin up, spin up, spin up in the 3 different orbitals, then spin down, spin down, spin down to complete each orbital box. And finally, we have 2 more electrons left, so we have a spin up, then a spin down in the 3s sublevel. So if these went well, great, we'll continue. If you're really lost, go ahead and look in the text, end of chapter questions, go ahead and try and a few more, check your answers, get the hang of this, or certainly get in touch with me if you're having real difficulties getting used to this format. So the boxes to depict the orbitals are nice. They give you a better view of all the electrons, but they're cumbersome. They take some time to make and to fill. So oftentimes, as busy scientists, we'll use electron configurations instead of those orbital diagrams. So the main differences would be an electron configuration lists the filled and partially filled energy levels in order of increasing energy. So that's similar to what we were doing already. But now we have the sublevels filling in order of increasing energy. That's the same. But instead of showing every electron as a spin up or spin down arrow, now we're using superscripts to show just the total number of electrons in each of the sublevels that have been occupied. And so we see here at the bottom for neon, neon has 10 electrons total. Of course, the 1s is completely filled, so instead of showing that box that we denote as 1s with a spin up and spin down, we just say 1s2 and understand that there's a spin up and a spin down there. We do the same thing for the 2s and then the 2p. Instead of showing the 3 boxes, up, 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 down, 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 instead we just show that there's a total of 6 electrons in the 2p sublevel. So it's much more convenient, but again, it relies on you having that understanding of how the electrons are in the orbital diagram. This is just a shorthand notation. So just to review, if we look at the 2 elements in period 1, hydrogen and helium, well, hydrogen's atomic number 1, meaning it has 1 proton in its nucleus, 1 electron outside the nucleus for a neutral hydrogen atom, therefore an orbital diagram with just a single spin-up arrow to represent an electron in the 1s, or for the electron configuration, that shorthand notation, we would just say 1s1. For helium, now we have element 2, 2 protons in the nucleus for a neutral atom of helium, therefore 2 electrons outside the nucleus, and an orbital diagram of spin up, spin down, a spin pairing there to fill the 1s, or if we want to use the electron configuration shorthand notation, it's a 1s2. Okay, so once you get the hang of it, it gets to be actually a lot of fun in my opinion, but it does take a little getting used to if you've never seen this sort of thing before, either the orbital diagram or the electron configuration, or both if you either had a long break from chemistry or never really got a firm foundation. Okay, if we move up to period 2, now we have lithium, the first member of period 2, which has 3 electrons, 2 of the electrons in that 1s orbital, and then 1 in the 2s. And it's really just that outermost energy level that we're focusing on for the chemistry of our elements. So the fact that it's got a half-filled 2s orbital means lithium's quite likely to give up that electron, and it reacts quite violently to do so. Beryllium has an additional electron, so now it's got a filled 1s and a filled 2s. That filled 2s gives it better stability than lithium, which had just a half-filled 2s. Boron now has 5 electrons, so it's our first element that has an electron in the p orbitals in its ground state. Carbon, with another electron, now has the 2 in the 1s, the 2 in the 2s, and now 2 in the 2p, although unlike the 1s and the 2s, those 2 in the 2p aren't in the same orbital box together. They're separate in 2 distinct p orbitals, where we half fill all the p orbitals before we go back and spin pair. So the electron configuration's already shorthand notation, but still, as very busy scientists, we need an even more abbreviated configuration. So I hinted at it just a little bit ago when I mentioned that the electrons in that outermost principal energy level are the ones that are really responsible for almost all the chemistry that goes on. So instead of listing every single electron energy level and the number of electrons present, we typically look at just the noble gas that precedes the element that we're interested in, and we put that symbol in brackets to denote that we have the same core as, in this example here, neon. So instead of writing 1s2, 2s2, 2p6, we can just write neon in brackets there, and that is understood, therefore, that we have all of the electrons that are present in neon, which would be the 1s2, 2s2, 2p6, and then we can just go on to talk about, in this case for chlorine in our example, it has 2 electrons in the 3s sublevel and then 5 electrons in the 3p. So we would abbreviate our notation to just say that the core is like neon, and that's a neon's element symbol in brackets there, followed by 3s2, 3p5. So it's much easier to see the electrons that actually matter and to just understand that the rest are buried in the core, not doing any real chemistry for us. So if we look here, now we have the elements that make up period 2. We can see their orbital diagrams and we can see their electron configurations, and now we can even go a step further. It doesn't help so much here because we're just replacing the 1s2 with helium symbol in brackets, but as we go on into later periods in the table, obviously it saves us quite a bit to replace neon or argon with just the element symbol instead of having to say 1s2, 2s2, 2p6, so on and so forth. So hopefully you've got a decent handle on all of this. If you are struggling, like I said, please let me know. And now we can see the period 3 configurations where we have neon. That does save us a fair deal of time to just put neon in brackets there instead of saying 1s2, 2s2, 2p6, writing that each time. And obviously as we go further down, it gets even more convenient to use that notation. So we're still out of the d orbital configuration so far because we have to go into period 4 to see that. Obviously there are 3d orbitals, but nothing being filled yet as we're in period 3. Okay, so alright, I think it's a good time now for a learning check. Alright, so here we have some multiple choice questions, good practice for the exam. Number 1 says the correct electron configuration for nitrogen is, and then pick it out from those. These are the complete electron configurations, not the abbreviated case for this particular learning check. Number 2, the correct electron configuration for oxygen is, and hopefully if you could get nitrogen, you can find oxygen pretty easily. And then finally 3, the correct electron configuration for calcium is, and hopefully you can select the correct option there. Looking at say C, this answer choice C for number 3, 1s2, 2s2, 2p6, 3s2, 3p8, that should set off some red flags, right? 3p6 is as high as we go, so 3p8 is not possible. There's one you can eliminate right away. Okay, so if you haven't made all your selections yet, please pause the video, and then once you've made your selections, we'll see how you did. Okay, so for number 1, if we're looking for nitrogen, a total of 7 electrons, we should have a total of 7 when we sum all of our superscripts, so 1s2, 2s2, 2p3 is a total of 7. Choice C was the correct answer. Moving on to number 2, now oxygen has a total of 8 electrons, so we should just differ by the 2p superscript, and so here we have 1s2, 2s2, 2p4, choice B. And then finally number 3, we already talked about why choice C was a ridiculous option because it had 8 electrons in the p sublevel, which can only hold a maximum of 6. The issue there became figuring out between A and B which was correct, and it's actually B, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. You might be tempted to go right into the 3D, but of course, as we've mentioned already several times, the 4s is slightly lower in energy. It fills first, and therefore we would fill the 4s before moving back into the 3D. So after calcium, the next element, scandium, would go into the 3D sublevel, but calcium ends at 4s2. Let's try another learning check. Hopefully you're not having any trouble with this, but just in case, let's do another one here. Okay, so this learning check wants us to write the electron configuration and abbreviated configuration for each of the following elements. Number 1, chlorine, number 2, sulfur, and number 3, potassium. So we'll write that out completely, and then we'll start to get used to that abbreviated notation, which I think you'll all like very much. It saves quite a bit of time, especially as we have period 3 elements and beyond. Okay, so I forgot to tell you to pause it. Hopefully you remembered to do so. But number 1, chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. And then to save us some time and space, we can just abbreviate in brackets neon's element symbol, 3s2, 3p5. So instead of writing 1s2, 2s2, 2p6 for all of these, at least for chlorine and sulfur, we can just write in parentheses, in brackets neon. Right, sulfur differs, it's just 1 less electron, so it looks almost the same, except now we're 1s2, 2s2, 2p6, 3s2, 3p4, or the neon core in brackets, 3s2, 3p4. Potassium is a period 4 element, and here we save a lot of space by just using argon symbol, right? The complete electron configuration shows 1s2, 2s2, 2p6, 3s2, 3p6, then 4s1. All of that in front of the 4s1 can be abbreviated just with argon's core, the symbol in brackets, 4s1. So quite a nice succinct way to represent potassium compared with the complete electron configuration. Hopefully these are going well, and I'm sure you're all loving the abbreviated form. So if you are still struggling, though, of course, reach out to me, try some additional practice problems, but we'll go ahead and move on. Alright, now let's go back and relate these orbital types and position in the periodic table. So we talked about groups 1 and 2, or group 1A and 2A. That's the S block, because they're either filling or have filled. The column 1A or 1 is the group that is half filled in its S block, and group 2 or 2A and also, of course, helium, which really should be over next to hydrogen for this part, has just filled its S block. So you see a lot of chemical reactivity for group 1A metals and relatively less for the group 2A because they have the filled versus the half-filled sublevel. We skip over the 10 columns in the middle, right? Those are the transition elements. They're interesting and different, and we'll talk about them a little bit, but they don't do as predictable of chemistry as what we call the main group, those first 2 columns and then the last 8 in the table. So skipping over to those last 8 groups, group 3A to 8A or 13 to 18, those are the P block. Those elements are either filling or have just filled their P sublevels. Then as we look back at that 10 group intervening area, the transition elements, they're all in the sublevel that's 1 less than the principal energy level. So we don't see them until principal energy level 4, right? But they're actually the 3D for the first row transition elements. The lanthanides and actinides, as we said, that's the F block. They're tucked down below the table just to keep the table more compact. Otherwise, we'd have to spread it out 14 more columns, and that would be unwieldy. So we tuck them down below, but that's the F block, and of course they're 2 below, where the F orbital energy level is 2 less than the principal energy level. So we fill the 6s, then we start to fill the 4f. So the Ds are 1 less than the energy level they appear in. The Fs are actually 2 less than the energy level they appear in. And just showing that energy level diagram to remind us why that happens. Of course, nature works the way nature works, and it's the lowest energy gets filled first. So we fill the 4Fs after the 6S because the 6S is lower in energy. We fill the 5Ds after the 6S for the same reason. So just be careful. The energy levels are pretty predictable for S's and P's, but once we get to D's and F's, then things get a little out of whack. The D's appear 1 period later than you'd expect. The F's appear 2 periods later than you would first expect them. And our text gives us a guide to using these sublevel blocks, and of course they suggest that we first locate the element on the periodic table, then we write the filled sublevels in order going across each period, and finally complete the configuration by counting the the electrons in the unfilled block. So let's take a look at how we apply these guides in action. All right, so if we're looking at the periodic table to write the electron configuration for silicon, for instance, so first we find the block there, and so we see that silicon's in period 3, which means it must have a filled period 1 and 2, so the 1s2, 2s2, 2p6, and based on where silicon is in period 3, it's in the p block, so we know we're going to end with a 3p something, and if we count over, it happens to be the second element there, so it's filled its 3s, so that we should have a 3s2, and then we've got 2 electrons in the 3p, so 3s2, 3p6. And then we can write it all together to show 1s2, 2s2, 2p6, 3s2, 3p2, or if you like that abbreviated notation, we could show in brackets neon and then just say 3s2, 3p2. Okay, so just using that guide to help write electron configurations for any element you could find on the periodic table. And despite how interesting and important they are, we won't do a whole lot with the transition elements in this course, but we do remind you here with this graphic that the 4s orbital has lower energy than the 3d orbitals. So if we're looking at the electron configuration, the first time we encounter d orbitals in the ground state is after calcium. Scandium is our first d block element. So you can either do the 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, 3d1 for scandium, or we could just put argon in brackets and then just say 4s2, 3d1 as you see there for scandium, their element 21 in the table. And we just go along filling the D's, and then finally we go back to the P's afterwards once we get back into the P block with gallium element 31. Notice there are some unusual things happening. Chromium and copper, for instance, are exceptions to the rules. So that's one reason we try to steer clear of the transition elements. They do a lot of important chemistry, especially biological chemistry. You need some chromium and some copper and a lot of the other trace elements in order to have certain body functions work correctly. So they're important, but they're also doing some unusual chemistry that's a little beyond our scope. So we'll talk about them, but we won't focus as much on the transition elements or lanthanides and actinides as we do with the main group elements. Okay, so here we're applying that same strategy to write an electron configuration, this time for manganese. And if I did ask you about a periodic element that's in the D block, a transition element block, I would ask for a normal, typical one. I wouldn't ask for an exception like chromium or copper, for instance. So assuming that manganese is normal, we find it halfway through that first row of transition elements. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. It must have filled all of those period 1, 2, and 3 orbitals first. And then finally in period 4, we've filled the 4s, and we're 5 boxes into the 3d. So we should end as 4s2, 3d5. So we can either write the complete electron configuration there, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5, or we could look at argon as our core, and then 4s2, 3d5 for manganese. Okay, so before we leave this subsection of Chapter 3, let's do a few learning checks. Let's see how well we're mastering this material. So this learning check here, we have 2 questions. Number 1, what are the last 2 sublevel blocks in the electron configuration for cobalt? And then pick from choice A, B, or C. And number 2, what are the last 3 sublevel blocks in the electron configuration for tin? So go ahead, pause the video, and when you've made your selections, start it back up and we'll see how you did. Alright, so there you have it. For cobalt, the correct answer choice is choice C, 4s2, 3d7. Of course, we'd never see a P, 3p for instance, or 2p for that matter, being in with the last 2 sublevels, or the abbreviated notation for something in period 4, right? So you could have eliminated A for that reason. And also, if you remembered that the D's that we're filling are 1 less than the S that precedes them, you would have been able to eliminate the 4s2 4d7 option and correctly identify 4s2 3d7. For number 2, the correct answer choice was B, 5s2 4d10 5p2. And that's, again, making sure that you didn't fall for the trick with having the 5 Ds. So the Ds are always 1 less, the Fs are always 2 less than the principal energy level for the horizontal row in which you find a given element. Alright, with our next learning check, this time we're going to be using the periodic table to write the electron configuration and abbreviated configuration for each of the following elements. So number 1, zinc. Number 2, strontium, and number 3, iodine. So go ahead and pause the video, write those full and abbreviated electron configurations, and then start it back up and we'll see how you did. Alright, so the full electron configuration for zinc, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. It's the last element in the D block there in period 4, and so therefore it must have just finished filling its 3D sublevel. Or we could spare ourselves that first bit and just have argon in brackets and then follow up with the 4s2 3d10. For strontium, we're now in period 5, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, or we could abbreviate all that with just the krypton in brackets, and then finally 5s2 to end either the full or the abbreviated form. Finally, with iodine as our last question here in this learning check, we have another period 5 element. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. You can see how it's much more convenient to just write krypton in brackets rather than all of that. And finally, now looking at the period in which we find iodine, 5s2, 4d10, 5p5. Alright, hopefully that's going well. We've got one more learning check ahead of us before we end this subsection of Chapter 3. Alright, so for this final learning check of the subsection, we've got the question, or the order, I suppose. Give the element, the symbol of the element that has, and now we are looking at number 1, the abbreviated configuration argon core 4s2 3d6. Number 2, 4 3p electrons. Number 3, 2 electrons in the 4d sublevel. And then finally, number 4, the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. So these are all directions for finding these particular elements in the table. Take a moment, pause the video, get out your bare bones periodic table that you use for the exams here in the course, and see how you do selecting those elements. Start it back up when you've found them all. Alright, so hopefully for number 1, the element that has the abbreviated configuration argon 4s2 3d6, you identified correctly as iron with the chemical symbol Fe. Number 2, the element with 4 3p electrons is going to be sulfur, element symbol S. Number 3, 2 electrons in the 4d sublevel, that would be zirconium, symbol Zr. And hopefully you're just looking 2 rows over in the d sublevel, 4 rows over back for number 2 with the 3p electrons. And finally, the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Well, just like number 3 that was looking for 2 electrons in a d sublevel, we have titanium, but now it's the 3d instead of the 4d. So it's titanium's just 1 above zirconium. So hopefully you're really getting the hang of this. This is what's going to make you sound like a chemist, impress people like a chemist if you know your way around the periodic table. And we're also starting to talk about these electrons and how they behave, the orbital types that they inhabit, why there's greater reactivity in those group 1 metals, for instance. So this is an important sub-chapter, and if you are struggling, please do continue to challenge yourself with end-of-chapter questions, and certainly reach out to me for additional assistance. All right? We'll see you again for the last part of Chapter 3 on the next video.